Hey everybody, this is me doing the infamous number 19. This particular integral is quite useful to be able to solve because it relies on your ability to do just about everything we've ever seen. Not everything, it doesn't really use integration by parts, but it uses quite a lot of techniques at a very high level, and I'd really like to go over this just to make sure that we get those high level things before moving on to other topics. A lot of people don't seem to find these integration techniques very intellectually stimulating. I like to see that there are some intellectually stimulating parts to this. It's about manipulating substitutions, which is fundamental to just about every branch of mathematics that I can think of. There's something in it for everybody. There's also other little things here and there. Adding by zero, plenty of it. And these are things that everybody can benefit from. So I hope this is helpful to you. Without any other delays, let's get started. The first thing we're going to do is make a substitution. Now I'm looking at this integrand here, and I'm thinking, okay, it's a mess, first of all. I can't think of a simple way to attack this. I don't know what the antiderivative is off the top of my head just by looking at this. So my first strategy will be to say q is the cube root of x plus 27. Now there's a reason why I've chosen that. Obviously, choosing q equals x doesn't change anything. All I've done is flip the letters around. That doesn't help. I want to be greedy and select the ugliest part of this while maintaining just one variable because I'm going to be solving for that one x that I've saved. I don't want to take the entire integrand to be my substitution variable because then I'll have multiple x's to deal with, and that's just not pretty or nice. Also, in addition, I will, by doing that, isolate x. That would give me the entire denominator, and then I can then find a differential, which will give me dx. So let's do that. I'm going to cube both sides of that equation. I'm going to get q cubed is x plus 27, which then means that x is q cubed minus 27, and then from here I could find dx. dx is 3q squared dq. So what you'll notice immediately is that I have something for the entire numerator. That's all of this, which is here. I have something for the denominator, which is all of this right here. And I have something for my differential, which is right here. Sorry, I had to move my cat out of the way. Okay. So I have something for everything. The main thing here is that you'll often find teachers very annoyingly, I'll admit, say is don't mix your variables. And the reason is because one, it becomes super cluttered if you mix up your variables, and you're more likely, this is point number 2, you're more likely to ruin your problem. 3, it's actually incorrect to say that one equation is equal to another when your variables are mixed. You're introducing more variables, which means you're turning it into a multivariable problem, which we really don't want to do right now. So to stay at least a little bit logically consistent and get something that's correct and get something that's clean and something that's understandable, we want to have something to substitute for every element of this before we begin. Okay? Now that we do, let's go for it. Let me do some black. So that entire green section is just q. My dx is going to be 3q squared dq, and my entire denominator x becomes q cubed minus 27. Already this is looking better. So let me rewrite this as 3 times the integral of q cubed dq over q cubed minus 27, like so. All right. Here's where things get a little tricky. You look at this, you're like, oh my gosh, okay, I have to do a partial fraction decomposition, but first I have to do a long division. Actually, you don't need to do a long division. So one of the things that you want to remember is the oldest trick in a book, and that is adding by zero. So this is going to save us from having to do long division and partial fractions, etc., when we really don't need to. So if I had an extra minus 27 on top, I could cancel with the bottom and be done with it. But since I'm subtracting by 27 and I don't want to change the problem, I have to add by 27. Again, the reason why I did this in orange here this negative 27 and this positive 27 add up to 0 because I have no 0, or I just have a 0 there. Okay, I don't want to change my problem. Furthermore, if I group these up like this, then I can split up this integrand into two different things because I'm using the rule in case it's not obvious. A plus b over c is a over c plus b over c. And I'm going to split these up and get the following. 3 times the integral of just the number 1 dq, plus I'm going to have an 81 integral of dq over q cubed minus 27. Okay, I got the 81, in case it's not clear, from this 3 combined with this 27 to give me this 81. Okay, so this integral I'm going to highlight in, let's do blue, because I'm going to refer back to it later. Okay, and this integral I'm also going to highlight in blue. These blue integrals are going to be the things I'm going to collect and come back to later to plug back in. This is going to have a lot of different parts unwinding, so I just want to remember the parts that I'm going to split off from. Here I want to deal with that particular denominator. One thing you'll notice is that the denominator is q cubed minus 27, but 27 is 3 times 3 times 3. In other words, q cubed minus 3 cubed. This is the difference of two cubes, and we actually know how to split this thing up. We know how to factor this. So if I had a cubed minus b cubed, this should be a minus b, a squared plus ab plus b squared. I want to prove this result just because it looks like magic if you're not familiar with this sort of thing. So I'm going to do that up here. Let me rewrite that. A minus b times the quantity a squared plus ab plus b squared. Okay, so multiply everything by a first. So we're going to get an a cubed plus a squared b plus ab squared. And then multiply everything by the negative b. We're going to get a negative a squared b minus ab squared minus b cubed. And as you can see, these two will cancel, these two will cancel, and I'm finally left with the correct answer of a cubed minus b cubed. Okay, so that's how we split these things up. So if I had q cubed minus 27 cubed, 27, which is q cubed minus 3 cubed, this is q minus 3 q squared plus 3q plus 9. Okay. Here, we're going to take this portion, just the integral portion, and we're going to deal with that, and I'll plug it back in here at the end. Okay, we'll not forget the 81. So if I was to try to integrate dq over q cubed minus 27, that's the same thing as trying to find the integral of dq over q minus 3 q squared plus 3q plus 9, like so. But here, unfortunately, we have to do a partial fraction decomposition. So use parfrac. Parfrac is the old Maple code for, or current Maple code for partial fraction decomposition if you wanted to do that. So now it just becomes an algebra problem in trying to find a way to decompose this into partial fractions. So let's write it out. Okay, this can be written as the following: a over q minus 3 plus bq plus c all over q squared plus 3q plus 9. I personally don't like having these fractions. My objective is to always find a, b, and c here. I don't need all this mess, so I'm going to perform a variant of something called the Heaviside cover-up method, named after Oliver Heaviside. So I'm going to multiply everything by the denominator of the left in order to clear all fractions. So I'm going to get 1 is equal to a times q squared plus 3q plus 9. Hopefully my q's and my 9's look different enough. Plus bq plus c times the quantity q minus 3. Okay? This is so important. Let's do yellow. This is so important. I'm going to highlight this, and I'm going to drag it with me to the next page. Okay. Here, what you'll notice is this is a polynomial that's always going to be true regardless of what q is. A, b, and c are just constants, so no matter what q I plug in, this will be a true statement. So here's what I'm going to do. I'm observing this thing, and if I was to set q equal to 3, so I'll do this in a different color just to distinguish it from all the rest of the work that we're doing. If I set q equal to 3, most of my variables just vanish, and I'm going to be able to isolate a. So that's exactly what I'm going to do. So set q equal to 3, and I'll get 1 equals a times 3 squared plus 3 times 3 plus 9 plus, and just for the sake of completeness, I'll plug everything in just so you can see what's going on. 3 minus 3. Here, put this in parentheses. So this whole thing is just 0 because of the 3 minus 3 term. Well, that's great. This allows me to isolate a. So I'm going to have 1 equals a times, this is 9, this is a 9, this is a 9. This is 3 times 9, which is 27. That immediately implies that a is 1 over 27. Let's hold on to that. And let's switch colors. Let's do orange. All right. Next, I'm going to pick 0. I'm going to pick 0 because I'm looking at this over here, and I want to get rid of b. I already know a. This will allow me to isolate c if I do that. So that's my thinking right now. So set q equal to 0. That's my next objective. So I'm going to get, since I already know a, I'm going to plug in for a. I'm going to get 1 is 1/27. I have 0 squared plus 3 times 0 plus 9. Here I have a b times a 0 plus c, and then 0 minus 3. All right, let's clean this up a little bit. Let's move this here. Let's clean this up. Obviously, 0, 0, 0. A lot of this cleans itself up. I get 1 is equal to 9 divided by 27. Well, that's pretty simple. That's just 1/3. And then on the other side here, I have a negative 3c. It reduces to some nice little clean value. Here, if I subtract 1/3 from the number 1, I get 2/3 is equal to negative 3c, and so that immediately implies that c is equal to negative 2/9. Okay. Now, going back up here for a second, I've done 0, I've done q is 3. All I need to do is find b now. So I have c, I have a. Any number works. I'm going to stay small and pick the number 1. I could have picked any number really, but 1 is nice enough to work with, so I'll just do 1. Let's do this in a different color. Let's do green. So q equals 1. So, all right, so let's do this. 1 is equal to a times 1 squared plus 1 times 3. Is that right? 3 times 1, either way. Plus 9, plus we have b times 1 minus 2/9 because that's what c is, and then I have 1 minus 3. Okay? All right, so let's clean this up again. Here we're going to get 1 is equal to, now here inside of the parentheses we have a 9 plus a 1 plus a 3. That's 13. A, remember, was, I should have plugged that in from the beginning, is 1/27. So we have 13/27. It looks horrendous, but it's going to clean itself up very nicely in a moment. 1 minus 3, that's just negative 2 times b minus 2/9. Okay. 1 minus 13/27 is 14/27, which is equal to negative 2b times 2/9. Divide by 2. So we're going to get, divide by negative 2, we're going to get negative 7 over 27 is equal to b minus 2/9, and all we have to do is add 2/9 to both sides. 2/9 is the same thing as 6/27, so that immediately implies that b has to be negative 1/27. See, I told you it cleaned itself up. We get just factors of 27 essentially. A is 1/27, b is negative 1/27, and c is this negative 2/9. So combining it all together, we get the following. Remember our original fraction? Original fraction was 1 over q minus 3, q squared plus 3q plus 9. This ended up becoming 1/27 over q minus 3, okay, plus b, which is in green over there. We had a bx plus c, or bq plus c, so we have a negative 1/27 q minus 2/9 because c was 2/9 over q squared plus 3q plus 9. Okay. All right. This is pretty messy, I'll admit, but we can actually clean this up. So we're going to have to integrate this, obviously. We can factor out the 1/27 from the q minus 3, that's fine. We can also factor out a negative 1/27 from the numerator of the second term there on the right. And if we do that, we're going to get a 6 on top, because 2/9 is the same thing as 6/27. So if I factor out a negative 27th, we'll get something nice. So let me write that up again. We had dq over q minus 3, q squared plus 3q plus 9. So just for a moment, going back, that was all the way down there. That blue on the right, that's what we just ended up converting. Okay, that's going to be 1/27 integral of dq over q minus 3. I'm not going to integrate this because it's going to be a waste of time. It's going to be too cluttered, so I'm just going to hold on to these things. Minus 1/27 integral of q plus 6 over q squared plus 3q plus 9 dq. All right, let me highlight this in blue because I'm going to use this later. Also this, because we're going to be working with that right-hand side also. Okay. Here, it's going to be helpful to we're going to take this apart and move it over here. It's going to be helpful for us to complete the square on the bottom, and you're going to see why shortly. So let me rewrite that. Q plus 6 all over q squared plus 3q plus the number 9 dq. The way the integral is, you might be tempted to just say, hey, let's just make a substitution of the denominator. We're going to get a 2q plus 3. It almost looks like it fits, but it won't, mainly because the entire numerator does not quite work out that way. We're going to get extra factors coming out. So first, you're going to have to take my word for it for the moment. You'll see after I do this why we want to do this. Let's clean up the denominator and rewrite it as a completed square, or just complete the square. You're going to instantly be able to see what we want to substitute or what we want to add to the numerator when we do that. So here, complete the square. Okay. So leave the numerator alone. It's not bothering us right now. The denominator, we're going to have a q squared plus 3q. I'm going to have this plus 9. Just leave it off. I'm going to do the completing the square inside the integrand. Since my coefficient of q squared is 1, I'm going to look at the coefficient of q, take that number 3, divided by 2. Remember that number 3 halves. I'm going to square that. Now, plus 9/4 minus 9/4. Again, I don't want to change my integrand. Completing the square is just a fancy way of adding by 0. It just depends on what 0 you're adding. So we get the following. Q plus 6 over, here we're going to end up with q plus 3 halves, quantity squared, and then 9 minus 9/4. 9 is 36/4. So altogether we're going to have a plus 27/4. All right, Now I'm going to do a little bit of algebraic magic because I want everything to be nice and clean. I don't like fractions within fractions, personally. I'm a little neurotic like that. So I'm going to clean up all of these factors here. The 3/2 is what's mainly bothering me right now. So I'm going to multiply the cube by 2 over 2 and combine the denominators. So I'm going to get the integral q plus 6 all over, I'm going to have 2q plus 3 over 2 quantity squared plus 27/4 dq. Okay, so copy this, go to the next page. We can clean this up. We're going to get q plus 6 all over. Here we're going to have a 2q plus 3 squared plus 27. Both of those terms in the denominator have a 1/4 factor. If you distribute the square, you'll see that that 2 in the denominator there inside the parentheses becomes, talking about this, that 2 will become a 4. So both of those terms have a 4. 4 in the denominator is a 4 in the denominator of the denominator becomes a 4 on the outside in the numerator like that. Okay. So we're almost done. This is going to tell us exactly what we need. Let me rewrite this 27 in slightly different terms. The number 27, I think everybody will agree with me, is the same thing as a square root of 27, all of that squared. I'm putting it into this form because I'm anticipating a trig sub in a moment. Okay? So, in this particular form, if I wanted to pick my denominator to be my substitution variable, so I'll pick the letter t in a moment, maybe, or some other one, I'm going to have the 27 term is just going to vanish. It's not going to matter after differentiation. The rest of it is going to stay. So if I pick t equals 2q plus 3 squared plus 27, dt is going to be 2 times 2q plus 3 times the derivative inside, which is another 2 dq, like so. So what I want to do is maybe have I want my numerator to look like that. Now, I'm almost in luck. I have a 4 but not a 2. So I'm going to do a little bit of fancy multiplying. In fact, actually, I'm going to make my life a little bit easier. I'm going to leave this as a 2 because I already have a 4 in front of my integral. I'm going to divide by 2. I'm going to have a dt over 2. This will almost give me what I want. So, if I multiply everything out here, in the numerator, bring the 4 inside the integral. I'm going to have a 4q plus, now 6 times 4, obviously 24. Over here, I have a 6. So I'm going to have 24, but I only want 6 of that. So I'm going to have I want 6 plus 18. That was too big. Okay, I'm anticipating a substitution. This portion will give me the substitution variable at the cost of an extra 18. So we're going to have to split this up into 2 different terms in order to do a substitution, if that's what we wanted to do. So split. This is what we're going to get. We're going to get a 4q plus 6 dq all over 2q plus 3 squared plus the square root of 27 squared. Okay, that's the first one. Plus we're going to have an 18 integral of dq all over 2q plus 3 quantity squared plus the square root of 27 squared, like that. Now, for those that are a little bit careful, you would have identified this as an instant trig sub. The answer is going to be very nice. It's very pretty. It's going to give us something that we want. Up here, we've already done the substitutions and everything. So I'll do this in yellow for the moment. If I pick that to be t, Then dt over 2 is all of this, which I have already in my numerator down below over here. So I'm just going to go ahead and make that substitution. I'm going to have a 1/2 dt, and the entire denominator was a t. So that takes care of that. That was easy. And on this side, we have a similar sort of situation going on, except it's a lot easier. This 18, I'm going to turn that into a 9 and a 2. So I'm going to have a 9 times the integral of 2 dq, because I'm anticipating another substitution. 2q plus 3 squared plus 27 squared. Now if I set that 2q plus 3 inside the parentheses into some substitution variable, let's call it s, then my ds is going to be 2 dq. That takes care of that, and so I will automatically have a nice trig sub in a moment. So I'm just going to rewrite all of this. Let's copy and move it to the next page. I carried along an extra q with me. That's fine. So we're going to get 1/2 dt over t. Let's not jump the gun here for a second. If s is 2q plus 3, ds is 2 dq, which I have. So I'm going to have the following. Plus 9, let me rewrite that, plus 9 integral of ds over s squared plus root 27 squared. This is an instant trig sub. We can instantly calculate the antiderivatives, and we're pretty much done. All we have to do is just cascade backwards and start plugging things back in. So we have 1/2 ln of the absolute value of t plus 9 over root 27. This is the arctan integral. Okay. Now let's back substitute for both t and s. T was, remember back here, it was all of that in yellow. So I'm going to just back substitute that. That's going to be 2q plus 3 quantity squared plus 27. Plus, now 27 is 3 to the 3/2 power. So square root of 27 is 3 to the 3/2 power. Up there on top we have 3 to 2, so we have 3 to 2 over 3 to the 3/2. We're going to clean that up in a moment. S, remember, is just 2q plus 3. It's at the very top there on the screen. It's going to be 2q plus 3 all over, we're going to have a root 27 plus c. Okay. Before plugging other things back in, let's clean this up just a tiny bit. 2q plus 3 squared plus 27. You can actually expand that term. I'm not going to do that because, again, I've done the problem and I know something very ugly is about to happen. So I'm just going to leave it alone. So 3 to the 2 divided by 3 to the 3/2, that's going to be root 3. Arctan of 2q plus 3 over root 27 plus c. All right. This whole thing, let me do this in blue. This whole thing, what was this? Where did we get this from? What did we just calculate? Going back, all we've calculated was just that portion. So now I have to take all of this and multiply by negative 1/27. And then let's not forget the rest of this too. Positive 1/27 dq over q minus 3 and the integral of that. So I'm going to want to have 1/27. Now going back again, this integral is super simple. That's just going to be the ln of the absolute value of q minus 3. So that's pretty simple. I'm not going to spend too much time on that. So let's just include it. There you go. Again, going back for a second, now I want negative 1/27 times everything else I have on that same page. There it is. So I want negative 1/27 times 1/2 ln of the absolute value 2q plus, they're not equal. 2q plus 3 squared plus 27 plus root 3 arctan 2q plus 3 over square root of 27. Let's do all of this plus a new c. It's just a different constant. Eesh. But we're still not done. We have one more little bit to back substitute. But let's actually clean this up for a minute. Let me copy this. Move it to the next page. Okay. So, where did we get all of that? So, back here, that was this. Now, this is just that particular integral right there, which happened to be just that integral without the 81. So we have to multiply everything we have on the very last page by 81 and then tack on a 3q. So we're going to have 3q plus 81 times everything we have, so we can remember that. Okay. So we have, finally, almost, we have 3q plus, I think it was a plus, 81 times all of that. So I'm going to cheat for a moment. Put that there. Now, 81 times 27, that's pretty easy. That's just the number 3. So we saved ourselves some time by not having to distribute everything. So let's actually do that now. So we're going to have 3q plus, now, we're going to have a 3 ln of q minus 3 minus 3 halves ln of 2q plus 3 squared plus 27 plus 3 root 3 arctan of 2q plus 3 over root 27, all of this plus that arbitrary constant. And now we're almost done. Almost done. My question wasn't in terms of q. It was in terms of x. So going all the way back. Oh, okay, there we go. Going all the way back, q is that ugly thing. And you see now why I didn't distribute that other term and made it wider, because then I'd have to have a bunch of these terms there. So remember, recall q was the cube root of x plus 27. Now we're about to be done. Let's combine it all together. The integral of the cube root of x plus 27 divided by x dx equals